Okay, so we have this tool to do the EEG seizure prediction. We just run it. Yeah, we'll place the code eventually on the page as well. There's currently just the description of the results so far, so I'll go into them. It's a Flask application, so we have to run this Python code for it to actually work. I'm getting an error. Well, that's because I changed the folder structure. Let me check quickly the folder structure. So I have dataset. Let's just copy relative path. Yeah, most of the time is messing around with a dataset. Yeah, we can get rid of that. We don't need it. Let's try running it again. Let's still try to access the same folder or something. Okay, now it's running. Where are we? Let's check a JavaScript. Yeah, get rid of all that essentially everywhere. Get rid of it. Let's see how many times. Yep, just this two. That's fine, we can manage it. Right. Okay, so we have the data. So we have seizures and no seizures. We have a train, test, and validation datasets. So the data is already split for us. The data is available on this this link. It's on Zenodo. There's a link at the bottom of the page, so you can download. The dataset is Creative Commons attribution license. Yeah, so it's a CHB MIT ScalPG dataset. And so running this model on it, which we're getting some weird results from. Yeah, so originally it meant to. Yeah, so we have a paper. It's quite old, from several years ago. They were doing a training. There's a description. It's a convolutional neural network. Yeah, showing immerse potential. I don't know about that. Might actually have to rewrite this because we having all sorts of issues with it. But we'll get the robot. So updating the paths. Okay, we're actually running, because this instance of Visual Studio Code is running the Flask application, we actually have to run the pre-processing of the data, so training of the model in another instance of Visual Studio Code, and we get these results, which are not great. And okay, let's go for the model. So we have this code that does the training. And let's check that. Meant to save the output figure as well. Let's actually check that it does it. It does not. Meant to save the figure. Maybe when we close it, it will actually save it as well. But we will pop it into the robot quickly. Let's actually try closing it. Let's pop in the results in text form as well. Okay, so we have the results of the model. All the folders seem to be working correctly. So the training algorithm is able to fetch all the required data. Okay, but then we get this weird results. See image attached. If you can explain what's happening there, it will be great. The validation. Yeah, I really don't understand what's going on there, but for some reason the validation is pretty high, but the training didn't do anything. It kept going up and down to essentially 0. And also the final result of the training accuracy is 50%. So it's essentially performing at the chance level. Is that correct? Yeah, if you can explain all the results, that will be greatly appreciated. So we're trying to keep this model as close as possible to the original paper. If you can explain what was done in the original paper, that will be great, and any potential differences to the current script if we implemented it incorrectly or something. We also had some notifications and warnings in terminal. Yeah, if you can go over those, it's fine. Yeah, I'm okay with not using CUDA GPU at the moment. Yeah, I'll just use the CPU. It's a quick training, doesn't take long. There's not actually much data, but yeah, we'll actually like to eventually go into the details of how this training algorithm performing, perhaps breaking it into stages, and yeah, if you can suggest a further analysis before we actually change the model. Again, we would like to keep it as close as possible to the original paper, because we are just trying to reproduce the results at this stage, can you actually mention the difference between our output and the original paper results? Okay, can you actually mention, look up in the conversation above, what were the results from the original paper? What was the performance of the algorithm compared to what we get at the moment?
Based on the results you've obtained and the images you shared, it seems that your current model is struggling to converge properly during training. Here's an analysis of the situation. Analysis of the current model's behavior. 1. Training and validation accuracy. The training accuracy fluctuates wildly between epochs, sometimes dropping to near zero and then rising again, which indicates that the model is not learning in a stable manner. This suggests that the model might be having issues with either the optimization process or the data being fed into it. The validation accuracy, on the other hand, is relatively higher and more stable compared to the training accuracy. However, this high validation accuracy might not be a true reflection of the model's performance. Given the training accuracy's behavior, it's possible that the model is overfitting to the validation set, or that there's an issue with how the validation data is structured. 2. Training and validation loss. The loss also shows a zigzag pattern, particularly for the training data, which again indicates instability in learning. Typically, you'd expect the loss to decrease steadily as the model improves during training. The validation loss is relatively stable, but doesn't decrease significantly, indicating that the model might not be learning features that generalize well. 3. 50% training accuracy. The final training accuracy of 50% suggests that the model is essentially guessing at random, which makes sense in a binary classification problem. This means the model hasn't learned meaningful patterns from the training data. Potential reasons for these issues. 1. Data issues, imbalanced data. If your seizure and non-seizure data are imbalanced, e.g., one class significantly outweighs the other, this can lead to poor model performance. This might cause the model to perform poorly on the minority class. Data quality. Ensure that the images are of consistent quality and correctly labeled. Inconsistent data, e.g., mislabeled data, varying image quality, can confuse the model during training. 2. Model architecture. The model architecture you are using is relatively simple with two convolutional layers followed by max pooling and dense layers. While this is similar to what's described in the paper, it may not be sufficient for complex datasets like seizure detection, where the differences between classes might be subtle and require deeper networks to capture. 3. Optimization issues. Learning rate. A learning rate of 0.01 with SGD is standard, but in some cases, it might be too high, leading to oscillations during training, as seen in your accuracy and loss plots. Overfitting. Given the fluctuations in training accuracy, your model might be overfitting, especially if the dataset is small or not diverse enough. The high validation accuracy, in this case, might be due to the model learning noise or patterns specific to the validation set. 4. Training process. Data augmentation. While data augmentation is being used, the effect might not be sufficient to make the model generalize well, or the augmented data might still be too similar to the original data, thus not providing enough variation. Early stopping. Although early stopping is in place, the model might need more epochs or a different patience setting to stabilize the learning process. Comparison with the original paper. In the original study, the authors likely achieved a much more stable training process with a more consistent increase in accuracy and a decrease in loss over epochs. The final model should have shown a higher accuracy on both training and validation sets without the erratic behavior seen in your plots. Potential next steps. 1. Check data balance. Ensure your seizure and non-seizure datasets are balanced. If not, consider using techniques like oversampling the minority class or undersampling the majority class. Based on the comparison of your results with the original paper, there are some significant differences in the performance metrics and behavior of the model. Here's a breakdown of the key points. 1. Original paper's performance. Training accuracy, 91.89%. Validation accuracy, 88.17%. Test accuracy, 61%. The model in the original study performed well during training and validation, achieving high accuracy and maintained a reasonable level of accuracy on the test set, although the performance dropped, which is expected when dealing with cross-patient datasets. This indicates the model's ability to generalize well to unseen data. 2. Your current results. Training accuracy, fluctuating with extreme variation and hitting near zero at some points. Validation accuracy, also fluctuating, but with no consistent improvement over epochs. Final validation accuracy, 50%, which is no better than random guessing, chance level. Loss curves. The loss for both training and validation did not show the expected decrease and stabilization over time, further indicating issues with the model's learning process. 3. Key differences and issues. Learning behavior. The extreme fluctuations in training accuracy suggest that the model is not learning effectively from the data. This could be due to several factors, such as improper data handling, insufficient or overly aggressive learning rate, or data that is too complex for the current model configuration. Dataset handling. Ensure that the dataset is being pre-processed correctly and that there are no issues with how the images are being fed into the model. The warnings and errors you observed in the terminal suggest that there might be issues with the data generators or dataset iteration, which could be leading to suboptimal training. Model configuration. The original paper used a similar generic CNN model with stochastic gradient descent, SGD, as the optimizer, with a learning rate of 0.01, momentum of 0.9, and decay of 1e6. If your implementation matches this, then the issue might lie in the specific implementation details or differences in how the data sets are split and processed. 4. Terminal warnings. The warnings about CUDA and GPU libraries indicate that your model is currently running on the CPU. While this doesn't directly affect the learning ability of the model, training on a CPU can be significantly slower and might impact performance if the model is not adequately optimized for CPU usage. The warnings regarding data sequence and generator issues suggest that the model is not receiving the expected amount of data for each epoch. This could be due to improper configuration of the data generator or issues in how the dataset is iterated over during training. 5. Next steps. Debug data handling. Check your data generators and ensure that they are correctly configured to provide a consistent and complete batch of data to the model. Optimize model parameters. Consider revisiting the model's hyperparameters, especially the learning rate and batch size, to see if adjusting these might stabilize the training process. Incremental debugging. Introduce changes incrementally and monitor the results closely to identify which change has the most significant impact on the training process. These steps should help align your implementation closer to the results observed in the original paper. The code you provided is designed to train a convolutional neural network, CNN, for binary classification, distinguishing between seizure and non-seizure EEG images. Below is a detailed explanation of the code, highlighting the differences compared to the original study. Explanation of the code. 1. Imports and libraries. The code imports various libraries necessary for data handling, model creation, training, and visualization. The libraries include TensorFlow for neural network operations, PIL for image processing, NumPy for numerical operations, and Matplotlib for plotting results. 2. Parameters. IMB size specifies the image dimensions as 280, 274 pixels, which is based on the study. Batch size set to 16, which is also derived from the study. Epochs set to 15, corresponding to the number of epochs used in the study. Initial LR. The learning rate is set to 0.01, as per the study. 3. Directory setup. Paths are set up for training, validation, and test directories. The dataset is assumed to be organized with subdirectories for seizure and non-seizure images within each dataset split: train, validation, test. 4. Loading images. The load images from folder function loads images from a specified folder, resizes them to the specified IMG size, converts them to grayscale, and assigns a label: 1 for seizure, 0 for non-seizure. The function returns NumPy arrays of images and their corresponding labels. 5. Data preparation. The loaded images and labels are combined for seizure and non-seizure classes in both the training and validation datasets. The images are normalized by dividing pixel values by 255 and reshaped to include a single channel for grayscale images. Labels are one-hot encoded to be compatible with the softmax output layer of the CNN. 6. Model definition. The model is a sequential CNN consisting of input layer, accepts images of shape 280, 274, 1. Com2D layers, 2 convolutional layers with ReLU activation and 16 and 32 filters respectively. Max pooling 2D layers, 2 max pooling layers for downsampling. Flatten layer converts the 2D matrix output into a vector. Dense layers, 1 fully connected layer with 64 units, followed by an output layer with 2 units for binary classification and softmax activation. 7. Compilation. The model is compiled using the stochastic gradient descent, SGD optimizer with momentum and learning rate decay. Loss is computed using binary cross-entropy, which is appropriate for binary classification. 8. Data augmentation. An image data generator is used to apply data augmentation techniques like rotation, width and height shifts, and horizontal flips. This helps improve model generalization by artificially expanding the training dataset. 9. Training. The model is trained using the fit method with the training data generator, validation data generator, and specified number of epochs and steps per epoch. The training is monitored using 2 callbacks. Model checkpoint saves the best model based on validation loss. Early stopping stops training early if validation loss does not improve for 5 epochs. 10. Evaluation and plotting. After training, the model is evaluated on the validation set and the accuracy is printed. The accuracy and loss over epochs are plotted for both training and validation sets to visualize the model's performance. Differences from the original study. 1. Data preparation. The original study likely had different pre-processing steps, such as more sophisticated filtering or feature extraction from the EEG data before training. The current code uses simple resizing and grayscale conversion, which might not capture the necessary features for seizure detection as effectively as in the original study. 2. Model architecture. While the general structure, CNN, is similar, the original study might have used a deeper or more complex model architecture, e.g., additional layers, different activation functions, or more filters in convolutional layers. The original study might also have used a different optimizer or hyperparameters, which could explain differences in model performance. 3. Data augmentation. The types of data augmentation applied in the current code, rotation, shifts, flips, might differ from those in the original study, which could influence the learning process. 4. Training process. The original study might have used a different training schedule, including more epochs, a different learning rate schedule, or additional regularization techniques, like dropout in specific layers, which could impact the model's ability to generalize. 5. Evaluation. The original paper reported results on a separate test set, with test accuracy reported at 61%. Your current code reports only the validation accuracy and does not evaluate on a test set. To better match the original study, you would need to evaluate on the test set after training is complete. By addressing these differences and carefully analyzing the model's training process, you can better align your implementation with the original study's approach and potentially achieve more comparable results.
Yes, we have some differences to the original study. Yeah, the fact that we're using some sort of grayscale might be a problem. Why are we using grayscale to begin with? I don't know. The data is already pre-processed. All the images are in the same dimension, I'm pretty sure. We should double check and actually not do any pre-processing at this stage. So all the images will just rely on the folder names in the current dataset. We don't need to do anything with it at this stage. Yes, so the general structure of the convolutional neural network is similar, but we might have some differences. The original study might have had additional layers, different activation functions, or more filters in the convolutional layers. But we do have the paper. It doesn't mention any of those, so it has the description for what the model design was like. So why can't we just use that? So if we are using that, then why we are not getting the same results? And more of a philosophical question is, if there were other settings, a more complex model architecture was used, why is it not mentioned in the paper? Was the intention for it was for others not to be able to reproduce the results? So can we find all the settings necessary for reproducing the model in the paper itself? Yeah, we have a description of the dataset. We have the images from the paper early in this conversation, so we should go over them again. So if we have a different optimizer or hyperparameters, yeah, we need to dive deep, see what's different. We're still trying to replicate the original results. Yes, potentially we might later just try and improve the model. So we'll have essentially two separate training algorithms, one as close as possible to the description in the original paper, and another one which is actually like optimized based on the current dataset structure. Now the original study might have used a different training schedule, including more epochs, a different learning rate schedule, or additional regularization techniques like dropout in specific layers. But if we could extract all the details from the study and replicate it in our code, that will be great. If any of it is not mentioned in the study, we need to know about it. Can you check and let me know what's actually missing from the description in the original study? So the original paper reported results on a separate test set. Do we have it? Might not have it. The test accuracy reported at 61%. Anyway, we can essentially reach anywhere above 50%. So that's doesn't sound promising, does it? Can you also in one sentence just mention the results from the original paper, just so we keep it in mind all the time while doing this.
Let's break down your queries and the approach to align the current model more closely with the original study while also addressing your concerns. Grayscale conversion and image preprocessing. In the current code, the images are converted to grayscale, which might not be necessary if the original dataset was already preprocessed and formatted as required by the study. The grayscale conversion reduces the image's color information to a single channel, which could strip away useful features that the original study might have used if they worked with color images. If the images are already pre-processed and standardized in size and format in the dataset, it would indeed be more appropriate not to alter them further during training. You can skip the grayscale conversion and simply load the images as they are to maintain consistency with the dataset used in the original study. CNN architecture and differences in the study. The CNN architecture in your current code is relatively straightforward. If the original study's architecture is clearly described, you should replicate it exactly to avoid discrepancies. From your description, it sounds like the original paper does mention the architecture, but lacks detailed information about specific training settings, such as the optimizer or learning rate schedules. This absence might contribute to the differences in the results. If the study doesn't specify certain hyperparameters or training settings, it's possible the authors used default values or settings that they didn't document, which might lead to reproducibility issues. However, this isn't necessarily done to obscure replication. Sometimes certain details are overlooked or assumed to be common knowledge in the field. Reproducing the original study. To faithfully reproduce the original results, 1. Ensure all image preprocessing matches. Skip unnecessary preprocessing, like grayscale conversion, if the images are already in the required format. 2. Match the CNN architecture exactly. Replicate the architecture as described in the study. This includes the number of layers, filter sizes, activation functions, and pooling layers. 3. Use identical hyperparameters. Use the optimizer, learning rate, batch size, and epoch count exactly as mentioned. If these are not specified, start with common defaults used in similar studies. 4. Training schedule and regularization. If the study doesn't mention techniques like dropout or specific learning rate schedules, it's safe to assume they were either not used or the default settings were applied. Missing information in the study. After examining the provided images and text from the study, here's what might be missing. 1. Specific hyperparameters. The study might not mention the exact learning rate decay, momentum, or other hyperparameter settings used during training. 2. Data augmentation techniques. While some techniques might be mentioned, the exact parameters for augmentation, e.g. how much rotation, shift, etc., might not be detailed. 3. Optimizer details. The exact configuration of the optimizer, e.g. any special settings or modifications, might not be thoroughly explained. Performance results. According to the details you provided earlier, the original study reported a test accuracy of 61%. Your model, which is currently achieving around 50% accuracy, shows that it's performing at the level of random chance. This suggests that there's still work to be done in either aligning the model closely with the original or improving it for your current dataset. Next steps. 1. Cross-check and adjust. Go through the study and make sure every possible detail of the model's architecture, pre-processing, and training regimen is replicated as described. 2. Simplify the pre-processing. Remove unnecessary steps like grayscale conversion if the images are already prepared. 3. Test different configurations. If you're still not achieving the expected accuracy, consider testing different hyperparameter configurations or even a different architecture to see if the performance improves. If you can implement these changes and continue testing, it should help you get closer to the results reported in the original study.
Okay, so skipping the grayscale conversion and other preprocessing that we currently have in the code is a great idea. Yeah, I want to maintain consistency. I think the dataset is already pre-processed. Yeah, we would like to double check in the paper or the dataset description. I'll just pull it up next as well. I added the table from the study that actually has all the model configurations and the results. Yeah, if you can go over that would be great.
Let's go through the important details from the original study's model configuration and the dataset information to align your implementation with the original setup. Model configuration and results from the original study. In the original study, the model configuration is as follows. Epochs, 15, batch size, 16, optimizer, stochastic gradient descent, SGD. Learning rate, 0.01, decay, 1e6, momentum, 0.9. The model achieved the following performance: average accuracy, 91.89%, average validation accuracy, 88.17%, average training loss, 0.244, average validation loss, 0.1819, training time per epoch, 14 seconds, model size, 8.93 megabytes, H5 file. Hashtag dataset details. The dataset is pre-processed and divided into the following sets: training set, 240 seizure images and 240 non-seizure images. Validation set, 30 seizure images and 30 non-seizure images. Test set, 30 seizure images and 30 non-seizure images. Each image is likely to have been pre-processed before being added to the dataset. Therefore, applying additional pre-processing like grayscale conversion may not be necessary or could even negatively affect the model's performance. It's important to use the images as they are, especially since the original study likely worked with pre-processed data. Steps to align your implementation. 1. Skip grayscale conversion. Ensure that the images are used in their original color format instead of converting them to grayscale, as this aligns with the dataset used in the original study. 2. Model architecture. The architecture used in your current implementation is generally similar to that in the original study. However, to match the exact results, confirm that the activation functions, number of filters, and layers match those described in the paper. This paper doesn't explicitly mention these details, so ensuring they align is crucial. Hyperparameters. Ensure you match the hyperparameters exactly, especially the learning rate, decay, and momentum values. 4. Test set accuracy. The original paper reported a 61% test accuracy. Your implementation is currently below this mark, which suggests that tweaking the model to align more closely with the original setup, e.g. no pre-processing and exact hyperparameters, might improve performance. Summary. To replicate the results from the original study, avoid additional pre-processing like grayscale conversion. Match the model's architecture and hyperparameters exactly as described. Focus on using the pre-processed dataset directly without modifications. By aligning your implementation with these details, you should be able to achieve results closer to those reported in the original study.
Yeah, we're just trying to return the exact number of images in each folder. Doing something like this. Let's see if it's actually. Oops. Yeah, we have non-seizure train. Yes, we have 600 files all up. In 9 folders. Does 9 make sense? Yeah, we have 3 types of datasets: train, test, validation, and each has seizure and non-seizure folder in it. Yeah, I think it's also counting the outer folders. Let's just get it generating. I'll answer any questions in the chat if you have any. Just let the robot just let it do some work. So the train dataset should have 240 images for each seizure and non-seizure types. And above is the structure of the whole dataset. So can you just in text explain in full sentences? We will generate the code later. There was a question while it's generating. There was a question about, so I have, where can they find the code? Yeah, always asking about the code. I mean, we have all the prompts. The code, well, the code probably won't work. When code is needed, it's actually on the page, but that's only for blocks that are not actually deployed. The music generation, so we have 2 types of music generation. We had the one from gesture music generator, and we have one that turning EEG into music as well. Where is it? Somewhere. Yeah, EEG music. So in both cases, from memory, yeah, the applications are heavily relying on JavaScript, so all the code should be just on the site. But the description should have all the prompts. So if you're trying to replicate it, just using the prompts should just do the job.
The dataset you provided has a specific structure divided into training, validation, and test sets, each containing images categorized as either seizure or non-seizure. According to the dataset description, the training set should have 240 images for each of the seizure and non-seizure categories. However, the provided directory listing reveals a potential issue with the dataset distribution, which could be contributing to the errors you've been encountering. Detailed breakdown of the dataset. 1. Training set. Seizure images. Should contain 240 images, but based on the structure provided, it seems like there may be discrepancies in the actual count. Non-seizure images. Similarly, this set should also contain 240 images. 2. Validation set. This set is used for tuning model hyperparameters and preventing overfitting. It typically contains a smaller, balanced subset of images from both seizure and non-seizure categories. The count in the dataset structure appears correct, but it would be wise to double-check the exact counts. 3. Test set. The test set is used for final evaluation of the model after training. Like the other sets, it should have a balanced number of seizure and non-seizure images. The listing shows the structure but does not specify exact counts. Issues to address. Dataset imbalance. If any of the directories do not contain the expected 240 images, this could result in the kind of errors you're seeing. The imbalance would lead to a mismatch in the number of images and labels during model training. Data loading functions. The existing data loading functions should correctly count and load these images, matching the expected number of labels. Given the error message from your previous attempt, there may be a mismatch between the images and their corresponding labels, particularly if images are missing or extra images have been added by mistake. Data integrity. Ensuring that all images are present and correctly labeled is crucial for training a reliable model. You might need to script a check to verify that each category has the exact number of images required. Next steps. 1. Verify image counts. Use a script to count the images in each directory and compare these counts with the expected values, 240 images per class in the training set. 2. Check image and label matching. Ensure that each image has a corresponding label and that the arrays used in training are of equal length. 3. Rebalance or correct the dataset. If there are discrepancies, you may need to either balance the dataset by removing extra images or investigate why some images are missing. Once these checks are done, you can proceed with generating the updated code, ensuring that it correctly handles the dataset as intended. This will likely resolve the issues you encountered during the model training process.
Okay, that sounds like a great idea. Can we verify image count? The dataset should be balanced as it is. I checked it manually, but if we can do it in Python code, perhaps within the same training script, that would be great. The image label is just the name of the subfolder. So we have train, test, and validation folders, and within each we have seizure and non-seizure folders. Is that clear?
To ensure that the dataset is indeed balanced and to automate the verification of image counts within the training script, we can incorporate a section of code that checks the number of images in each folder, seizure and non-seizure, for the train, validation, and test datasets. Since the image labels are determined by the folder names, we can easily count and categorize the images programmatically. Here's a conceptual explanation of how you can implement this. 1. Count images in each folder. For each main folder, train, val, test, loop through the subfolders, seizure, non-seizure. Count the number of images in each subfolder and store these counts. 2. Check for balance. Compare the counts between the seizure and non-seizure folders within each main folder, train, val, test. If the counts do not match, you can raise a warning or log an error indicating that the dataset is not balanced. 3. Output results. Print the number of images found in each category, seizure and non-seizure, for the train, validation, and test sets. This can be done either before or after the model training to ensure the dataset is balanced before proceeding with the training process. By adding this verification step directly into your training script, you can automate the process of ensuring that the dataset remains balanced, which is crucial for maintaining the integrity of your model's training and evaluation processes. Here's an updated version of your Python script that includes the functionality to verify that the dataset is balanced by counting the files in each folder. This updated script will count the number of images in the train, val, and test folders for both seizure and non-seizure categories, and print out the results to confirm that the dataset is balanced before proceeding with the training process. Python import OS, import numpy as np from pyl, import image, import
Yeah, let's actually do it in a separate, as a separate script. Okay, and why didn't I see it before? No, I did see it. What's the problem? Okay, can you specify what the problem might be? We have a balanced data set. The labels are just the names of the folders for where the image is located. So that's what should be used for labels. Can you confirm in text what's going on without including any code?
The error you're encountering indicates a mismatch between the number of images, x.shape, and the number of labels, y.shape. In your dataset, xtrain contains 640 images, while ytrain only contains 480 labels. This discrepancy suggests that the images and labels were not correctly aligned during the loading process. Since you have confirmed that your dataset is balanced and that the labels should correspond directly to the names of the folders, i.e., seizure and non-seizure, the issue is likely due to an incorrect combination of the image arrays from the two categories, seizure and non-seizure. It is possible that either more images were loaded than expected, or that the labels weren't assigned correctly, leading to the mismatch. The labels should indeed be created by assigning a label 1 for seizure and 0 for non-seizure, based on the folder from which each image was loaded. The issue arises when the total count of images in your xtrain array does not match the total count of labels in ytrain. Given the situation, the key points to verify are: 1. Loading process. Ensure that the images are being loaded correctly from each folder and that the corresponding labels are assigned correctly for each image. 2. Concatenation. Ensure that when the image arrays from seizure and non-seizure categories are concatenated, the corresponding labels are concatenated in the exact same order and length. By addressing these aspects, the mismatch between the images and labels should be resolved, ensuring that both X-train and Y-train have matching lengths. Given the nature of the error you're encountering, it might be more efficient to regenerate the code from scratch. This will ensure that all aspects of the data loading, processing, and training pipeline are consistent, correctly aligned with your dataset structure. Regenerating the code allows for a fresh start, eliminating potential issues carried over from previous iterations of the code. In this case, regenerating the code would involve 1. Loading the dataset, properly counting and validating the number of images in each folder, train, validation, and test to ensure they match the expected numbers. 2. Label assignment, accurately assigning labels based on the folder structure, seizure for 1 and non-seizure for 0. 3. Data processing, ensuring that the images are loaded with the correct dimensions and that no additional pre-processing, like grayscale conversion, is applied unless specified by the original study. 4. Data concatenation, confirming that the concatenation of images and labels is performed correctly, leading to matched lengths of the X-train and Y-train arrays. 5. Model architecture, revisiting and accurately defining the model architecture as described in the original study, ensuring that all hyperparameters and training settings are consistent. 6. Training and validation, incorporating proper steps for data augmentation and ensuring the training process is set up with the correct steps per epoch and validation steps. This approach will provide a cleaner, more controlled environment to work in and will likely prevent the type of mismatch error you're currently experiencing. If you agree with this approach, I can proceed to regenerate the code with these considerations in mind. The issue with the labels likely stems from how the data is being concatenated or handled after loading the images. Despite the number of images being correct, there seems to be a mismatch between the number of images, xtrain.shape0, and the number of labels, ytrain.shape0. To resolve this, we can add print statements to inspect the content of the labels and ensure that they match the images exactly. Let's go through the process step by step, updating the code to include error detection and monitoring throughout the execution. I'll provide you with a regenerated version of the script, including checks that print out the labels and additional information to help diagnose the issue. Updated Python script with error detection and monitoring. Python import OS. It seems that the issue persists due to a mismatch in the dimensions of the images and labels. The discrepancy in the output indicates that the image tensor x.shape and the labels y.shape are not aligned as expected. The x.shape shows a shape of 640, 280, 274, 3, whereas y-shape shows 482. This discrepancy likely arises because of how the data is concatenated or processed after loading. It seems like there might be additional steps or incorrect concatenation that causes this mismatch. Next steps. 1. Print out labels. We need to add specific print statements to check the content and length of the labels at different stages in the code to ensure they match the image tensors correctly. 2. Check image channel handling. The image tensor shape suggests that there might be an extra channel or some inconsistency with the image data being loaded, causing a mismatch in shape. This could happen if some images are being loaded with an alpha channel, or if there's an inconsistency in how the images are read or processed. 3. Verify image and label pairing. Ensure that the process of loading and pairing images with their labels is correct and consistent. We need to verify that every image loaded corresponds to the correct label. Code update. Let's update the code to include print statements to check the actual content of ytrain, yval, and ytest before proceeding to the data generator. The issue seems to be related to the way the labels why train, why val, why test are being assigned and used in the script. Here's what's happening based on the output you've provided. Observations. 1. Label values. All the labels in why train, why val, and why test are showing as 1. This indicates that the label assignment is not alternating between 0 for non-seizure and 1 for seizure, as expected. This is a key issue because it means the model is not learning to differentiate between the two classes. 2. Image shapes. The image data shape 480, 274, 284 suggests that the images are loaded with an additional channel. This fourth channel might be an alpha channel that should not be there. 3. Data label mismatch. The shapes of X train and Y train should match in the first dimension, number of samples. The error you're encountering happens because of the mismatch, likely because the concatenation or assignment process for labels didn't handle the two classes, seizure and non-seizure, correctly. Action plan. 1. Label assignment issue. Revisit the code where labels are assigned to ensure it properly assigns 0 for non-seizure images and 1 for seizure images. 2. Image channels. Ensure the images are correctly processed without unnecessary channels. Typically, for color images, you should have 480, 274, 280, 3, or for grayscale images, 480, 274, 280, 1. 3. Revising the code. You should review the process of loading images and assigning labels to ensure they correctly reflect the two classes. Additionally, ensure the one-hot encoding of labels only happens after all labels are assigned correctly. Possible code changes. Without regenerating the entire code, here are the critical sections that might need updating. Ensure that when you load images from the folders, you correctly alternate between assigning 0 for non-seizure images and 1 for seizure images. Double-check that the images are loaded with the correct shape, either stripping out the unnecessary alpha channel or processing them as expected. If you want to regenerate the code with these observations in mind, it would be a more robust approach to ensure no errors carry over. But these steps should guide you in addressing the specific issue you're facing. It looks like your model training has completed, and the results are as follows. Train accuracy. The training accuracy fluctuated significantly across epochs, which suggests potential instability during the training process. Validation accuracy. The validation accuracy showed some fluctuations, but it peaked at around 79.17% in the ninth epoch. Test accuracy. The final test accuracy was around 50%, which is not very high and suggests that the model is not generalizing well to unseen data. Issues noted. 1. Fluctuating accuracy and loss. The significant oscillations in the accuracy and loss during training and validation suggest that the model might be struggling to learn a consistent pattern from the data. This could be due to several reasons. Overfitting. Your model might be overfitting to the training data. However, the significant fluctuations in accuracy indicate that it could also be underfitting or suffering from unstable training. Learning rate. The learning rate of 0.01 might be too high, leading to erratic updates to the model weights, causing the oscillations. Batch size. The batch size of 16 is relatively small and could lead to noisy gradient estimates, contributing to the observed fluctuations. Model complexity. The current model architecture might be too simple for the complexity of the task or not well tuned. Recommendations. 1. Learning rate. Consider reducing the learning rate, perhaps to 0.001 to stabilize training. 2. Batch size. Experiment with a larger batch size, such as 32 or 64, to reduce the noise in the gradient estimates. 3. Model architecture. Evaluate adding more convolutional layers or increasing the number of filters per layer to capture more complex patterns in the data. 4. Regularization. Introduce regularization techniques like dropout, already included, and L2 regularization to reduce overfitting. 5. Data augmentation. Ensure that your data augmentation strategy is diverse enough to help the model generalize better. Would you like to implement these suggestions or explore alternative approaches?
Before we explore how to improve the model, can we actually make sure we bring back the counting of the number of images in each sub folder? And we want to make sure the loading of the images and sorting them out by the shapes are correctly established. Can we do it in the code? We would like a confirmation in print text when the code is executing.
The updated code you've shared should correctly print out the labels and ensure they are appropriately assigned. Running this will allow you to see the distribution of labels, 0 for non-seizure and 1 for seizure, in your training, validation, and test sets. By confirming that both 0 and 1 labels are present, you'll be able to verify the integrity of your dataset and ensure that the model is receiving balanced input. Additionally, normalizing and one-hot encoding the data will prepare it for training, and the printed shapes will confirm that everything is structured correctly before proceeding. If you encounter any issues with the outputs, especially if the labels still show a discrepancy, that would be the next point to investigate further. Otherwise, if the labels look correct, you should be ready to continue training the model or explore further optimizations. It looks like the model is now running with the correct dataset and labels. However, the accuracy results are fluctuating and remain low, which suggests that the model might not be learning effectively. Here are some steps to consider for improvement. 1. Double-check data augmentation and shuffling. Ensure that the data is shuffled correctly and that the data augmentation process is not introducing any issues. This can sometimes cause fluctuations in accuracy if the batches are not properly randomized. 2. Adjust the learning rate. The learning rate might be too high, leading to large updates that prevent the model from converging. Try reducing the learning rate to see if it stabilizes training. 3. Increase epochs and patience. Training for more epochs and using early stopping with patience might help the model learn better. The current settings might not allow enough time for the model to converge, especially if the learning rate is reduced. 4. Investigate the network architecture. The current architecture might be too simple to capture the nuances in the data. Consider adding more convolutional layers or increasing the number of filters in the existing layers. Also, experimenting with different activation functions, like ReLU, leaky ReLU, etc., could help improve the performance. 5. Evaluate the model's performance with different metrics. Accuracy alone might not be the best metric, especially if the classes are imbalanced. Consider using metrics like precision, recall, F1 score, or ROC AUC to get a better understanding of the model's performance. 6. Regularization techniques. Introduce regularization techniques like dropout, L2 regularization, or batch normalization to prevent overfitting and improve generalization. 7. Inspect the data quality. Ensure that the data set does not have mislabeled images or any artifacts that might be confusing the model. By implementing some of these adjustments and carefully observing the changes in the model's performance, you should be able to improve the model's accuracy and stability over epochs. To double-check the data augmentation and shuffling processes, we'll need to ensure that the data is being handled correctly throughout the loading and pre-processing stages. The following points outline how you can ensure that the data augmentation and shuffling are performed correctly. 1. Shuffling data. Ensure that the data is shuffled correctly both during the loading process and within the data generator. If the data isn't shuffled properly, the model might see patterns within a batch that do not generalize well, leading to fluctuations in accuracy. The image data generator class has a shuffle parameter that should be set to true to shuffle the data before each epoch. Additionally, ensure that shuffling is done after splitting the data into training, validation, and test sets to prevent any information leakage. 2. Data augmentation. While using the image data generator, make sure that the augmentations are consistent with the nature of your data. For instance, augmentations such as rotation range, width shift range, height shift range, and horizontal flip should be applied in a way that maintains the integrity of your EEG spectrogram data. Confirm that augmentation is only applied to the training set and not to validation or test sets, as this can artificially inflate the validation accuracy and lead to misleading results. 3. Validation. After setting up the data augmentation and shuffling, validate the data by visualizing a few examples after augmentation. This step can help ensure that the augmented data still represents valid and meaningful examples of the original data. 4. Code check. Here's an updated code snippet that ensures data shuffling and augmentation are correctly handled. Python, define the data augmentation generator. DataGen equals image data generator, rotation range equals 20, width shift range equal 0.2, height shift range equal 0.2, horizontal flip equals true, fill mode equals nearest. Ensure the data is filled appropriately after augmentation. Prepare the training data generator with shuffling train generator equals datagen.flow xtrain ytrain, batch size equals batch size, shuffle equals true. Ensure that validation and test sets are not augmented or shuffled. Val generator equals image data generator. Flow xval, yval, batch size, shuffle equals false. Test generator equals image data generator. Flow xtest, ytest, batch size, shuffle false. Now train the model history equal model train generator, validation data equal val generator, epochs, steps per epoch len xtrain, batch size, validation
luck with this data set. No, there is a misunderstanding. There is a misunderstanding. I meant the output images. So the performance of the model after training, the performance of the model should be stored in an image in the current folder. Yeah, we're training again. We're like trained 10 times already. And no, doesn't. It's still test accuracy. It's still at 50%. So that's not great, is it? Yeah, just performing at the chance level at the moment. Trying to figure out what might be wrong. We're using an AI to train an AI, but it's not having much luck. So trying to distinguish essentially between these images, it should find the difference between them. So you can see some different lines in the spectrogram. Okay, can we make sure everything that we are generating in this code is saved into the same folder? And yes, we would like to troubleshoot the whole code. We want to make sure the images are loaded correctly, that they are split. Well, they're already split into the folder, so that should be fine. So I'm not sure why do we need augmentation at all. Can we try have an option to turn augmentation and shuffling off, just to see if it makes any difference? Yeah, the steps per epoch and validation steps should be fine in theory. I think some of it is taken from the original paper. If we can double check, that would be great. And some of it is just common values used in these cases. So that should be fine, is it? Okay, so we currently augmentation and shuffling are turned off. Didn't seem to make much difference. Can actually turn them on, maybe one by one. So we turn the augmentation on. Have to close this image for the thing to actually start running. Yeah, the accuracy is below 50%. 0.4, 0.57, 0.6. Yeah, 0.48. So it's going back down. So that's why it's stopping as well. It's not improving by much. If we turn shuffling, on as well. The accuracy 0.54, 0.6. Yeah, 0.5. Yeah, it's not going up. 0.51, 0.62. Yeah, it keeps fluctuating, but it's not really going up. So the training is not doing much. No, but the validation is better, even if the training didn't do anything at all. This says test accuracy is at 0.86%, which is weird. But that's a result with both augmentation and shuffling turned on. But training doesn't seem to actually do much. We will publish these results on the website, so it should be available for you to check out.
It looks like the model performed significantly better with shuffling and augmentation turned on, as indicated by the final test accuracy of 86.67%. The earlier fluctuations in ACK loss during training were likely influenced by the absence of these techniques. Key points. 1. Data augmentation. Augmentation artificially increases the size of the dataset by creating modified versions of images, which helps in improving model generalization and reducing overfitting. Since your dataset might be relatively small, augmentation is crucial in providing the model with varied data. 2. Shuffling. Shuffling ensures that each batch during training has a mix of different classes. Without shuffling, the model might encounter batches with similar data consecutively, which can lead to poor generalization and fluctuations in training. 3. Storing results. The final model performance, including accuracy and loss graphs, should be saved to the specified folder //BioniChaos sites rhythm scan. This ensures that all outputs from the training process are well organized and accessible. Next steps, experimentation. You might want to run further experiments by toggling the augmentation and shuffling options to see their direct impact on performance. Hyperparameter tuning. Consider adjusting learning rates, batch sizes, or even experimenting with different network architectures to further enhance performance. Review original paper. If this setup is derived from an original study, double-check the methodology to ensure that your implementation closely follows their approach, particularly with respect to augmentation, shuffling, and steps per epoch. Would you like to continue with more fine-tuning, or perhaps explore another aspect of the model?
Okay, I think we're actually getting somewhere now. So this is results. Okay, can you explain the following results? Looking at the image attached, and this is with the following settings. Seem to make a lot of difference. Not sure why. If you can explain all this using continuous sentences and full paragraphs without any code, that would be great. Okay, we're actually getting somewhere, which is good. Yeah, I'll keep track of what we have done. We trained the model with about 7 or 8 different scripts, but now it's doing something useful.
The results you're seeing indicate significant fluctuations in model performance, which can be attributed to the effects of data augmentation and shuffling settings. With augmentation turned off and shuffling turned on, the model's performance shows a substantial improvement in accuracy and a corresponding decrease in loss, especially when compared to earlier runs with augmentation enabled. Model performance analysis. 1. Initial training and validation accuracy. In the first epoch, the training accuracy is approximately 55%, while the validation accuracy is about 48%. This suggests that the model is learning some patterns but is not yet generalizing well to unseen data. 2. Improvement across epochs. As training progresses, the model's performance steadily improves, with training accuracy eventually reaching nearly 100% by the 9th epoch. Validation accuracy also improves, peaking at 100% by the 8th epoch and remaining high thereafter. This suggests that the model is fitting well to the training data and generalizing better to the validation data. 3. Overfitting signs. One concern is potential overfitting, as indicated by the high training accuracy coupled with perfect validation accuracy in some epochs, followed by a drop in validation performance toward the end, as seen in the 13th epoch. Overfitting occurs when the model learns the training data too well, including noise and minor variations that don't generalize to new data. 4. Final test accuracy. The final test accuracy of 96.67% indicates that the model performs well on unseen data, although this is slightly lower than the validation accuracy during training. This is a good sign as it suggests the model's performance on real-world data might be reliable. Explanation of settings. Impact. Data augmentation off. By turning off data augmentation, the model trained directly on the original dataset without introducing any artificial variations. Data augmentation typically helps in generalizing the model by simulating new data points, but in this case, turning it off might have prevented the model from seeing noisy or unrealistic variations, leading to a more stable training process. Shuffling on. Shuffling ensures that the data is fed to the model in a random order during each epoch. This helps the model generalize better by preventing it from learning the order of the data, which might otherwise lead to overfitting. Shuffling appears to have contributed to the model's improved performance by ensuring diverse batches during training. The combination of these settings, disabling augmentation and enabling shuffling, appears to have led to better learning dynamics, where the model could effectively learn and generalize from the provided data. The high final test accuracy confirms that these settings resulted in a well-performing model. However, the slight overfitting noticed suggests that some regularization techniques or careful monitoring of validation performance might be necessary in future runs to ensure consistent results across different datasets or variations.
Yeah, why do I have a feeling? Hey, why do I have a feeling I won't be able to reproduce these results? So this is the code that we currently have. We would like the model to make sure the model is actually saved. Not sure. We need to confirm it's actually saving at the moment. Yeah, this is the code that we currently have. But yeah, we just like to improve it slightly. Otherwise, these settings seem to do something useful. even though the training is fluctuating quite a bit. I think we already explained it, but I don't fully understand why does that happen. But then the validation accuracy is quite high and loss is quite low. But the training is a bit weird. And we need... So the number of epochs should be fine, but there might be other parameters. Yeah, we need to make sure the model is saved in the current directory. Yeah, do we have this? We do model save. I don't see it. Seizure detection final model. Maybe if I close the image. Yeah, there's something weird with the memory. Something's up. Yeah, my file browser is still like loading stuff, which is a bit odd. Is the code executing fully even if the image, the plot of the results, the performance of the model is open? The code actually finish executing? It looks like. Or because the model is not being saved. Well, it's being saved, but I don't see it. Yeah, there's a folder problem. There's a folder problem. Yeah, it's saving the final model and best model and the accuracy loss PNG into the wrong folder. Can we make sure it is saving it into... Yeah, we need to sort out the folders. Hey, can you go over it? We need to sort out the folders. Can you? Yeah. Wrong button. Context. It's been good so
Based
far.
on the code you've shared, it appears that the model training and evaluation process is functioning as expected. However, there are a few key areas to improve and ensure that everything runs smoothly, particularly regarding the saving of the model and plots to the correct directory. Issues and suggestions. 1. Saving files to the correct directory. The code is attempting to save the model and plots in a specific directory, /BioniChaos/rhythmscan/. The issue might stem from how the file paths are being constructed, particularly when using the tilde sheesh to represent the home directory. The tilde is a shell-specific shorthand and may not be correctly interpreted when constructing file paths programmatically in Python. Solution: replace the tilde with the full path to the directory or use os.path.expanduser to correctly expand the tilde to the full path of the home directory. 2. Model checkpoint and saving. The model checkpoint callback is being used correctly to save the best model during training. However, ensure that the model is saved with a file extension that matches the format you're intending to use. You've specified .keras in the file names, which is appropriate for the Keras model format. Solution: ensure that the final model and checkpoint models are being saved with the correct extension and that the directory paths are correct. 3. Training fluctuations. The fluctuations in training accuracy and loss you are observing could be due to several factors, including a small dataset size, batch size, learning rate, or the inherent randomness in data shuffling. These fluctuations are not uncommon, especially with a small dataset or when the model is trained for a limited number of epochs. Solution: to reduce fluctuations, consider increasing the batch size, fine-tuning the learning rate, or experimenting with different data augmentation techniques. Alternatively, increasing the dataset size, if possible, could also help stabilize training. 4. Ensuring reproducibility. To reproduce results consistently, ensure that random seeds are set across all libraries, NumPy, TensorFlow, etc. This will help ensure that the model's training process is consistent each time you run it. Solution: set random seeds at the start of your script. Python import NumPy as NP, import TensorFlow as TF. Import random np.random.seed42, tf.random.setSeed42, random.seed. Updated code snippet. Here's how the updated code might look to address the file saving issue and ensure everything runs as intended. It seems like your model is now showing some interesting results, though there are fluctuations in the training accuracy and loss curves, while the validation accuracy and loss remain more stable. Let me address each of the points you mentioned and suggest some next steps to further refine your model. Understanding the current results. 1. Training fluctuations. The fluctuations in the training accuracy and loss curves could be due to several factors. One common cause is the use of a small batch size, 16 in your case, which can lead to high variance between batches, especially when the model is trained on a relatively small dataset. This high variance can cause the model to have drastic changes in accuracy and loss from one epoch to another. Another factor could be the learning rate. Although you are using a learning rate recommended by the study, it might still be too high for your specific dataset, causing the model to oscillate rather than converge smoothly. 2. Validation performance. The validation accuracy and loss show a much more stable trend, which is good. This stability indicates that your model is generalizing well to unseen data, which is often more important than having stable training curves. However, the discrepancy between the training and validation curves, particularly the fluctuations in the training data, might suggest overfitting to some batches or a model that hasn't yet fully converged. Next steps. 1. Adjust the learning rate. Consider reducing the learning rate slightly to see if it smooths out the training fluctuations. You can start with a reduction by a factor of 2, e.g. from 0.01 to 0.005, and observe the impact on the training process. 2. Experiment with batch size. Increasing the batch size might help reduce the variance between batches, leading to smoother training curves. You could try increasing it to 32 or 64, depending on your hardware constraints. 3. Data augmentation and regularization. Although you turned off data augmentation, it might be beneficial to experiment with it again, especially if your model starts to overfit as you reduce the fluctuations in training. Adding dropout layers in the model architecture could also help by providing regularization. 4. Learning rate schedules or optimizers. Implementing a learning rate schedule, e.g. learning rate decay or using a learning rate scheduler, can help the model converge more smoothly. Alternatively, experimenting with different optimizers like Atom, which adapts the learning rate during training, might yield better results. 5. Increase training epochs. Since your model is starting to perform well after 15 epochs, you might want to extend the number of epochs to see if the performance improves further. Early stopping with a patience parameter will prevent unnecessary overtraining. 6. Model checkpoints and saving. Ensure that your best performing model is being saved correctly. From the code, it seems you've correctly configured the model checkpoint callback. Make sure that the paths are properly expanded using os.path.expand user to avoid issues with saving files to the intended directories. Code improvements. Ensure correct paths. You've already made sure that the paths are expanded correctly using os.path.expand user, which is great. Reproducibility. You've set the random seeds for NumPy and TensorFlow, which will help in reproducing your results. Regularization. Consider adding dropout layers after the fully connected layers to prevent overfitting. Given these points, your model seems to be on the right track, and with a few more tweaks, you could improve its stability and performance further. Keep iterating, and you should be able to refine your results even more. It seems like you've been making some good progress in refining your model. Let's break down the current situation. Key points and observations. 1. Learning rate adjustment. You've recently adjusted the learning rate to 0.005, which has affected the training dynamics. The learning rate is a critical parameter, and reducing it can lead to more stable training, but might require more epochs for convergence. 2. Training fluctuations. The training accuracy is showing significant fluctuations, which is indicative of potential overfitting or the model struggling to find a consistent pattern. This could be due to several factors, including batch size, shuffling, or the inherent variability in your data. 3. Validation performance. The validation accuracy is consistently high, which is a positive sign. It suggests that your model generalizes well to unseen data despite the fluctuations in training accuracy. 4. Model saving and paths. You mentioned concerns about the model and performance plots being saved in the correct directory. The current code uses os.path.expanduser to ensure that paths are correctly expanded to the user's home directory. This should ensure that files are saved correctly in the //BioniChaos site/rhythmscan/ directory. 5. Epochs and training. The number of epochs, 15, seems appropriate given your current settings. However, the fluctuations suggest that more epochs might be necessary to stabilize the training process, especially with a lower learning rate. Next steps. 1. Model stability. To address the fluctuations in training accuracy, consider the following. Increase the batch size. This could help smooth out the training process, as larger batches tend to give a more accurate estimate of the gradient, reducing the noise in the learning process. Regularization. Adding techniques like L2 regularization or dropout layers could help reduce overfitting and make the model more stable during training. Learning rate scheduling. Implementing a learning rate scheduler could help by reducing the learning rate as the training progresses, allowing the model to fine-tune its weights more delicately. 2. Validation accuracy. The high validation accuracy is a good sign, but ensure that this is not just a case of the model memorizing the validation set. Continue to monitor this closely as you tweak other parameters. 3. Model saving. Ensure that the paths for saving the model and plots are correct and consistent throughout your code. The use of os.path.expanduser should work, but double-check that the files are indeed being saved where you expect them. 4. Additional testing. Once you have a model that seems to perform well, consider running it on completely unseen test data, if available, to ensure that it generalizes well beyond the validation set. 5. Documentation and reproducibility. Given the fluctuations and the changes you've made, make sure to document all the parameters and settings that led to the current results. This will help you or others reproduce the results later. Number 6. Further experimentation. If the model is still not performing as expected, consider experimenting with different architectures or even different types of models, e.g., deeper networks, different activation functions to see if that improves stability. By addressing these steps methodically, you should be able to further refine your model, stabilize training, and ensure that your results are reproducible. It seems like you've been experimenting with different parameters such as learning rate and batch size while training your model, and you're observing some fluctuations in training and validation accuracy and loss across epochs. Observations. 1. Training fluctuations. The training accuracy and loss are highly fluctuating across epochs. This indicates instability in the training process, which could be due to several factors like an inappropriate learning rate, small batch size, or the nature of the data. When the learning rate was set to 0.005 and batch size was 32, the model showed different patterns of instability. Reducing the learning rate usually stabilizes training, but may also slow down convergence. 2. Validation accuracy and loss. The validation accuracy sometimes reaches high values, even approaching 100%, with corresponding low validation loss. This suggests that the model is capable of fitting the data, but is overfitting or not generalizing well. Overfitting could be a concern here, as indicated by the sharp drops in training accuracy loss, but consistent high validation accuracy loss in certain epochs. Steps for improvement. 1. Learning rate adjustment. Try lowering the learning rate further, e.g. 0.001. A lower learning rate can help smooth out the fluctuations and potentially provide a more stable training process. However, keep in mind that too low of a learning rate might slow down the convergence. 2. Batch size exploration. The batch size of 32 seemed to reduce the fluctuations to some extent, but you might want to explore a few more batch sizes, e.g. 64 or 128, to see if a larger batch size could further stabilize training. 3. Data augmentation. Since you had augmentation turned off, enabling it might help improve generalization by introducing more variability in the training data, reducing overfitting. However, if augmentation is unnecessary based on your specific application, it's okay to keep it off. 4. Early stopping and checkpointing. You're already using early stopping and model checkpoint, which are good practices to avoid overfitting and save the best model. Ensure these are configured optimally with appropriate patience and monitoring metrics. 5. Cross-validation. If not already done, you might want to perform cross-validation with different splits of your dataset to ensure that the model's performance is consistent and not an artifact of a particular split. 6. Regularization. Adding dropout layers or L2 regularization might help in reducing overfitting, especially if the model is very complex or the dataset is small. 7. Model complexity. Evaluate if the model is too complex for your dataset. Simplifying the model, e.g., reducing the number of layers or filters, might help in achieving better generalization. Final thoughts. The key is to achieve a balance between model complexity and generalization. Fluctuations can often be a sign of an overly aggressive learning rate, small batch size, or a model that is not suited to the data's complexity. Iteratively adjusting these parameters and monitoring the results is the best approach to converge on an optimal setup. It looks like you've been experimenting with different training configurations, such as adjusting the batch size, learning rate, number of epochs, and whether to apply augmentation. The results you've shared reflect these changes, and it's evident that certain settings produce different behaviors in the training and validation accuracy and loss plots. Here's a summary of what might be happening and the possible next steps. Training fluctuations. 1. Learning rate adjustments. The initial learning rate, LR, is a critical parameter. A high LR can cause the model to oscillate, leading to the erratic training accuracy and loss observed in your plots. Lowering the LR can stabilize training but might require more epochs to converge. Your recent adjustments from 0.01 to 0.0005 show some improvement in stability, but fluctuations are still present. You might consider lowering it further or using a learning rate schedule that decreases the LR as training progresses. 2. Batch size. Smaller batch sizes often introduce more noise during training, which can cause fluctuations in accuracy. A larger batch size smoothens out these fluctuations but may require more memory and longer training times. Comparing the performance with batch sizes of 16 and 32, you see some differences in stability, especially in the validation accuracy. Batch size adjustments are a trade-off between noise and stability. Finding the right balance is key. 3. Data augmentation. Turning on augmentation can help the model generalize better by introducing variability in the training data. This generally improves validation performance at the cost of slightly longer training times. From your recent results, enabling augmentation seems to help with validation accuracy, but this is highly dependent on the dataset and the specific augmentations applied. 4. Shuffling. Shuffling is generally recommended to prevent the model from learning spurious correlations in the data. It should always be on, especially when the data is ordered or has some pattern that could bias training. Recommendations. 1. Learning rate tuning. Continue experimenting with smaller learning rates. Alternatively, implement a learning rate scheduler that reduces the LR on a plateau, particularly when the validation loss stagnates. 2. Early stopping and checkpointing. Ensure your model checkpointing is saving the best model according to validation loss. This way, even if the model starts to overfit or destabilize, you have a good checkpoint to revert to. Early stopping with a patience parameter can help terminate training once the validation performance no longer improves. 3. Fine-tuning batch size. Since your results show fluctuations, try an intermediate batch size, like 24, to see if it stabilizes the training while not requiring too much memory. 4. Augmentation refinement. Fine-tune the augmentation parameters. For instance, reducing the rotation range or shift range slightly might help if the model struggles to generalize with more aggressive augmentations. 5. Additional epochs. If the model is showing signs of improvement but not yet fully converged, increasing the number of epochs might help, particularly if the learning rate is reduced. 6. Hyperparameter tuning. Consider using hyperparameter tuning techniques, like grid search or random search, to explore different combinations of the parameters mentioned above systematically. In summary, the model is on the right track, but further fine-tuning and stabilization techniques are required. The fluctuations could be minimized with careful learning rate adjustments, appropriate batch sizes, and the right amount of data augmentation. It seems like you're observing fluctuations in your model's training and validation accuracy, even after tweaking several hyperparameters like the learning rate, batch size, and data augmentation settings. Let me explain what's happening and provide some suggestions for next steps. Understanding the fluctuations. 1. Training fluctuations. The wild fluctuations you're seeing in training accuracy could be attributed to several factors. Since your model's training accuracy dips to 0 in certain epochs and then spikes back up, it suggests that your model might be struggling with instability during training. This could be due to the small dataset, high learning rate, or the batch size being too small to generalize well across the dataset. With small datasets, models tend to overfit easily, and the training becomes highly sensitive to small changes in the data or model weights. Number 2. Validation accuracy. The validation accuracy is performing much better than the training accuracy, which is quite unusual. Usually, the validation accuracy should be somewhat lower than the training accuracy due to overfitting. However, the observed high validation accuracy could indicate that the model is learning features that generalize well to the validation set, but are overly simplistic or too specific to the validation data, rather than capturing more complex patterns. 3. Loss fluctuations. The loss function also fluctuates, which further supports the idea of instability in your model. With the current settings, your model might be jumping around in the loss landscape rather than smoothly converging towards a minimum. Next steps to improve stability. 1. Lower the learning rate. You've already tried lowering the learning rate to 0.005, but consider reducing it even further to 0.001 or 0.005. A lower learning rate can help your model make smaller, more stable updates to the weights during training, leading to smoother convergence. 2. Increase the batch size. You've tried batch sizes of 16 and 32. If your system's memory allows, you might want to try even larger batch sizes, like 64 or 128. Larger batches can provide a more stable estimate of the gradient and help reduce the fluctuations. 3. More epochs. Although you've tried running for 15 and 30 epochs, your model might benefit from even more epochs, especially if the learning rate is reduced. This would allow the model to train longer and potentially find a more stable solution. 4. Regularization techniques. Consider introducing regularization techniques like L2 regularization, weight decay, or dropout layers, if not already implemented. Regularization can help reduce overfitting and improve the generalization of your model. 5. Balanced data. Ensure that your dataset is balanced in terms of the number of seizure and non-seizure images. Imbalances can cause the model to favor the majority class, leading to misleading accuracy metrics. 6. Cross-validation. Use k-fold cross-validation instead of a single train test split. Cross-validation provides a more reliable estimate of model performance by training and validating the model on different subsets of the data. Reproducibility. To ensure reproducibility of your results, set random seeds. Continue setting random seeds for both NumPy and TensorFlow. This ensures that your experiments are deterministic, meaning that you should get the same results every time you run the code. Save intermediate models. Saving the model at each epoch allows you to revisit specific points in the training process and compare different models more effectively. Document changes. Keep track of every change you make in your hyperparameters or model architecture. This helps you understand the impact of each change and avoid confusion if you need to reproduce or refine your results later. Final considerations. It's important to note that model training, especially in deep learning, often requires iterative experimentation and tuning. The fluctuations you're seeing are a normal part of this process. By systematically tweaking the parameters and observing the results, you'll gradually move towards a more stable and high-performing model. If you implement the above suggestions and still experience issues, consider revisiting your data pre-processing steps or even exploring different model architectures. For instance, a deeper or more complex model might capture the underlying data patterns better, although this comes with the risk of overfitting on smaller datasets. Observations on training fluctuations and model performance. Training fluctuations. The fluctuations observed in the training accuracy and loss are a clear sign that the model is experiencing instability during training. This can happen for several reasons. 1. Learning rate. The learning rate is a crucial hyperparameter that controls how much to change the model in response to the estimated error each time the model weights are updated. A higher learning rate can lead to larger updates, causing fluctuations in the training process. In your case, the final reduction to initial LR equals 0.001 seems to have stabilized the training to some extent, but fluctuations still persist. The batch size is another important factor that influences the stability of training. A smaller batch size might cause the model to converge more slowly, but with better generalization. However, it can also lead to noisier updates and thus fluctuations in training metrics. Increasing the batch size to 32 seemed to have reduced some of the noise, but not entirely. 3. Data augmentation. The use of augmentation can sometimes introduce variability into the training process. However, since augmentation was set to false in your final trials, it doesn't appear to be the cause of these fluctuations. Validation performance. The validation accuracy being consistently high and the validation loss remaining relatively low indicate that the model is performing well on the validation set. This is a positive sign, suggesting that despite the instability during training, the model is learning useful features and generalizing reasonably well to unseen data. Recommendations. 1. Stabilize training. While the learning rate of 0.0001 is showing promise, you might want to experiment further by using learning rate schedules or adaptive learning rates, like Atom Optimizer, that can adjust the learning rate dynamically during training. This could help in stabilizing the training process further. 2. Early stopping and checkpointing. You are already using early stopping, which is a good make sure that the model checkpoint is saving the best performing model on the validation set rather than the last epoch, as this will ensure you retain the best model even if the training continues to fluctuate. 3. Evaluate over multiple runs. Given the fluctuations, it's important to run the training process multiple times to ensure that the observed performance is consistent and not just a result of random variations. You should look for consistency in the validation accuracy across different runs. 4. Investigate the data. It might also be worth revisiting the data pre-processing pipeline to ensure that the data is balanced and well prepared. Any imbalance in the dataset can lead to skewed performance, especially if one class is much larger than the other. 5. Consider ensemble methods. If fluctuations persist, and if you're observing good validation performance, you might consider training multiple models and using an ensemble approach. This can often lead to more stable and reliable predictions. 6. Visualize misclassifications. It would be helpful to visualize some of the cases where the model is making errors to understand if there are patterns in the misclassifications. This might give insights into whether the model needs more data, better augmentation, or perhaps more complex architectures. Next steps. Fine-tune the learning rate and batch size further to find the optimal balance. Run multiple training sessions to check the stability of your results. Visualize the misclassifications to gain insights into the model's weaknesses. Consider advanced techniques like learning rate schedules or adaptive optimizers to improve training stability. By following these steps, you can continue to refine your model and improve its performance. The training and validation accuracy graphs you've shared show significant fluctuation across epochs, especially in earlier epochs, with a learning rate of 0.0001 and a batch size of 64. Let's break down what might be happening and the steps you could take next. Observations. 1. Training accuracy and loss. The training accuracy shows an upward trend, albeit with some fluctuations, which is common in training processes, especially with a high learning rate or small dataset size. The training loss decreases steadily, which is a good sign that the model is learning. 2. Validation accuracy and loss. The validation accuracy fluctuates a lot, especially in the initial epochs, but tends to stabilize in the later epochs. The validation loss shows a downward trend, indicating that the model is generalizing well on the unseen validation data. However, the fluctuations in accuracy suggest that the model may not be entirely stable. Possible reasons for fluctuations. Batch size. Larger batch sizes, like 64, generally lead to smoother and more stable gradients during training. But in this case, the fluctuations might indicate that the model is still struggling to converge consistently, possibly due to the small dataset or high complexity of the task. Learning rate. A learning rate of 0.001 is quite low, which should generally lead to more stable training. However, if combined with other factors like a small batch size or noisy data, it might cause the model to struggle in consistently finding the best path for convergence. Data augmentation. Since augmentation is off, the model is seeing the same images repeatedly, which can sometimes cause the model to overfit to the training data, leading to discrepancies between training and validation metrics. Next steps. 1. Increase epochs. The model might benefit from more epochs to fully converge. Consider running it for 30 epochs to see if the fluctuations stabilize. 2. Adjust batch size. You could try further adjusting the batch size, maybe testing with a smaller batch size like 32 to see if the model behaves differently. Batch size impacts how noisy the gradient updates are. Smaller batches can lead to noisier but sometimes more effective learning, depending on the dataset. 3. Data augmentation. Consider turning augmentation back on. Augmentation can help the model generalize better by introducing slight variations in the training data, which might help reduce the fluctuations in validation accuracy. 4. Learning rate scheduler. Implement a learning rate scheduler that reduces the learning rate after a certain number of epochs without improvement. This can help the model fine-tune its weights as it approaches convergence. 5. Early stopping. Continue using early stopping, but perhaps with a slightly longer patience to allow more epochs for potential stabilization. 6. Cross-validation. If possible, try cross-validation instead of a single-train validation test split. Cross-validation can provide a more robust measure of how well your model generalizes and can help identify issues like data leakage or a poor trained test split. Summary. The model is showing potential, but the fluctuations suggest it might not have fully converged yet. By experimenting with the epochs, batch size, data augmentation, and learning rate, you can potentially improve the model's stability and performance. Monitoring the accuracy and loss over these experiments will help you find the optimal setup. To visualize the misclassifications made by the model, you can plot some examples from the test set where the predicted labels do not match the true labels. This will help you understand the types of errors the model is making and whether there are any consistent patterns in these errors. Here's how you can implement this. Steps to visualize misclassifications. 1. Evaluate the model on the test set. Use the model to predict the classes of the test images. 2. Identify misclassified images. Compare the predicted labels with the true labels to find the misclassified cases. 3. Plot misclassified images. Display a few of these misclassified images along with their true and predicted labels. Implementation. Here's a Python script that will do this. Python import matplotlib.pyplot as To visualize and understand the misclassifications made by your model, you can follow these steps. 1. Identify misclassified examples. After evaluating the model on the test set, you can predict the labels of the test images and compare these predictions with the true labels. Misclassified examples are those where the predicted label differs from the true label. 2. Visualize misclassified images. Display the misclassified images along with their predicted and true labels. This can give you a sense of whether the model is confusing specific types of images or if there's a common characteristic among the misclassified images. 3. Analyze the patterns. Look for patterns or commonalities among the misclassified images. For example, you might notice that the model struggles with certain types of images, like those with noise, certain angles, or specific features. Example code for visualization. Python import matplotlib.pyplot as plt, import numpy as np. Predict on the test set predictions equals model.predict xtest. Predicted labels equals np.argmax predictions axis 1. True labels equal p.argmax ytest axis 1. Find the misclassified examples, misclassified indices, np.where predicted labels equal true labels. Plot misclassified images. Looking at the results from your training session, it seems that your model is showing improvement over time, especially with the validation accuracy stabilizing at a high level. Here's a breakdown of what's happening and some suggestions for further improvements. Observations from the training. 1. Early fluctuations. Initially, the model accuracy for both training and validation fluctuates significantly, which is expected during the early stages of training as the model is adjusting its weights. 2. Improvement over time. Over the epochs, both training and validation accuracy show an upward trend, with validation accuracy eventually reaching very high levels, close to 100%. This indicates that the model is learning well and generalizing to the validation set. 3. Validation loss. The validation loss decreases steadily, which is a good sign. It suggests that the model is not overfitting and is improving its performance on unseen data. Potential issues and next steps. 1. Batch size and learning rate. You've tried various batch sizes and learning rates, and the current setup with a batch size of 64 and a learning rate of 0.001 seems to work well. If you observe further fluctuations or instability, you might consider fine-tuning these hyperparameters. Misclassifications. As previously mentioned, it would be beneficial to visualize the misclassified examples. By examining these, you can determine if the errors are due to data noise, class imbalance, or inherent difficulty in certain examples. 3. Early stopping and model checkpoint. You're already using these callbacks, which is great. Continue monitoring these checkpoints to ensure that you're capturing the best model during training. 4. Further augmentation. If the model is still overfitting or not generalizing well to the test set, you might need to increase data augmentation. Introducing more variations during training can make the model more robust. 5. Regularization techniques. If the model starts overfitting as you increase epochs, consider adding dropout layers or L2 regularization. 6. Explore deeper architectures. Given that your model is performing well but still has room for improvement, exploring more complex architectures like deeper convolutional neural networks, CNNs, or even pre-trained models like VGG or ResNet might yield better results, especially if you have a larger dataset. 7. Fine-tuning and transfer learning. If you decide to use a pre-trained model, fine-tuning it on your specific dataset could further improve accuracy. Actionable steps. 1. Visualize misclassifications. Implement the code snippet provided earlier to visualize and analyze misclassified examples. 2. Monitor training. Continue with the current hyperparameters while keeping an eye on overfitting as the number of epochs increases. 3. Experiment with deeper architectures. Once you've fully explored the current model's potential, consider experimenting with deeper networks or transfer learning techniques. By following these steps, you'll likely gain more insights into the model's behavior and continue improving its performance. The images you've provided show instances where your model is consistently misclassifying images with a true label of 1 as 0. This type of error analysis is crucial for understanding the limitations of your model and where it might be struggling. Based on these visualizations, here are some steps and considerations you might want to explore further. 1. Increase model complexity. If the misclassifications are occurring because the model is not complex enough to capture the subtle differences between classes, you might want to consider adding more layers, increasing the number of filters in your convolutional layers, or even trying more complex architectures like ResNet or VGG. 2. Data augmentation. Although you currently have augmentation turned off, it might be worth turning it on and experimenting with different augmentation strategies, e.g. rotations, flips, zooms, and shifts, to see if it helps the model generalize better. Augmentation can help the model learn more robust features that aren't dependent on specific image orientations or slight variations. 3. Class imbalance. If there is a significant imbalance between the two classes, the model might be biased towards predicting the majority class. This can be mitigated by techniques such as oversampling the minority class, undersampling the majority class, or using class weights during training. 4. Regularization. Adding dropout layers or L2 regularization can help prevent the model from overfitting, which might be causing the model to perform well on training data, but poorly on unseen data. 5. Learning rate adjustment. You've experimented with different learning rates, but it might still be useful to employ a learning rate scheduler or use learning rate annealing to help the model converge better during training. 6. Evaluate confusion matrix. It could be beneficial to look at the confusion matrix to get a better sense of the types of errors your model is making across the entire dataset. This will provide a broader view than just visualizing misclassified images. 7. More data. If feasible, obtaining more data, particularly in the areas where the model is struggling, can provide the model with more examples to learn from and improve its predictions. 8. Review misclassified examples. Analyze the misclassified images in more detail to see if they have common characteristics. Sometimes the data itself might be noisy or mislabeled, leading to poor performance. Incorporating these steps should help in addressing the misclassification issues and improving overall model performance. You can experiment with each approach and observe its impact on your model's accuracy and loss metrics. The settings that provided the best results so far, based on the accuracy and loss curves, as well as the misclassification visualizations, are 1. Batch size, 64, 2 epochs, 30, 3. Learning rate, 0.001, 4. Data augmentation, off, 5. Shuffling, on. These settings yielded the highest validation accuracy, approximately 95%, with a corresponding test accuracy of 95%. The model demonstrated a good balance between training and validation accuracy, with the validation loss consistently decreasing over the epochs, indicating effective learning without overfitting. Additionally, the misclassification visualizations showed fewer errors, suggesting the model is generalizing well on the test data under these conditions. Therefore, these configurations are likely the most optimal based on the experiments conducted so far.
in the code, can we also output all the parameters, including model size, training time per epoch, average of validation loss, average of training loss, average of validation accuracy, and average of accuracy? We would like to eventually compare the output of our script to the original paper from several years ago. Yeah, the bot might just give a summary for the thing. Unless there's any specific questions. Yeah, we have to update this text. So essentially we'll be doing a write-up of everything it does. We have the model, we have the performance, and no, it's not this one. We had it doing pretty well. Yeah, we had something like this. And a final performance of about 91, 95. I think we reached 95 at some stage. And we have the model itself. I don't know why it's so big. It's 74, almost 75 megabytes. The original model from the paper was just under 9 megabytes. So not sure what happened there. Yeah, I might be publishing just the whole code, including the parameters. Yeah, I might display the results in a similar fashion as this table in the paper.
To modify your code to output the detailed performance metrics, including average accuracy, average validation accuracy, average training loss, average validation loss, training time per epoch, and model size, you can make use of TensorFlow Keras callbacks, along with some custom code to calculate and print these metrics after training. Below is an example of how you can implement these changes. Python import OS import NumPy
We'll see how we publish this stuff. Yeah, there's a few discrepancies between what we got and the results of the paper. You can also print out the current settings for the model. And the output of the terminal we would like to save into a text file. No, no. No. No, we actually want to modify the code. Don't want it to be executed on the OpenAI web server or something. We need everything locally. Yeah, so I have one code which has settings similar to the original study. And the second code has updated the parameters for the model. There might be other changes as well. That one is not actually being accessed, so I don't know why do we need it. We have the standard image size. Yes, so those will be the original model settings from the paper. Have tray validation test. Yeah, loading RGB. We're not doing a grayscale conversion anymore. So loading the images should be the same. Yeah, we're confirming that both 0 and 1 labels are present. It's important. That is important. And we're also confirming the dataset shape. Normalize and reshape the data. Encode the labels. Confirm encoding. Define the model, right? So yeah, we have the input layer, convolutional 2D, max pooling 2D, and now convolutional 2D, and now max pooling, flattening, dense 64 and dense 2. Compiling the model. Now this DK thing was supposedly discontinued or something, because I'm getting a warning for it. Might take a look at it later. So we currently not doing augmentation. I don't know, it just works better with no augmentation, even though the original paper did mention augmentation, but they didn't actually say how they do it. We do have shuffling turned on. We're saving the models. We do have early stopping, just so it doesn't run forever. Okay, now we have this tracking. Tracking training time. We need time. Import time. Okay, we do need to import time because we'd like to track the time it takes to train. Okay, we're training the model. That's the same. We are calculating the training time per epoch. Before saving the final model. Now, okay, we are evaluating the model, printing the valuation loss. Now over here we want to plot all these alpha results. And then actually plot the accuracy and loss of epochs. Should be the same. And we also display at the very end, we have another image that just shows the images that were misclassified. Bring it back. Yeah, so we have the data set, we have a train test validation, that's all working fine. And shall we retrain quickly? Just make sure that image. So this is what we get for the same settings as indicated in the paper. Okay, delete a previous versions. So we have, yes, 6 is close to the original study. Just call it train close to original study. And then we have a modify model parameters. So that's the results, result of the model with the paper settings from several years ago. I want to save the model name, the output name. With the name of this file. Should we just run it again? Yeah, we don't want to be running it forever, for too many times. Don't really need to save the model. We can just save the accuracy loss. Yeah, so that accuracy loss is for trained with the original paper model. That's right. And then we'll have another one, which is the AR updated settings. And this will be training for 30 epochs. Yes, we get quite different results. Can probably even run it for longer. Yes, I have no idea. Well, I do have an idea that those are different parameters, but essentially instead of a batch size of 16, 15 epochs, yeah, still augmentation is still turned off. Shuffling is turned on. Yeah, the initial learning rate is much lower. Then we have more epochs. So do we need more epochs? Well, yes, in this case. And batch size is 4 times larger. Should try it with 32. And what's the difference between should be printing out all the no, we're not. What we're meant to be printing. Yeah, we need more work on this. Might continue this next time, so I'll say bye. Go. Eventually everything I do appears on this website, as you know or do not know. So go check it out. There's a lot of interesting tools like this one, for example, a cochlea simulator. You can actually see how a cochlear implant works as realistically as possible, and you can even adjust some parameters. So go check it out. You can even increase or decrease the number of electrodes, so on and so forth. So lots of fun. And yeah, you can try hissing into it to actually see what the different sound make. So what the electrodes in the cochlea they actually activate, and change your filter parameters as well. So go play around with it. On the site will be links in the comments and everywhere everywhere else. See you in a bit.